And I am happy. A morning, Dr. M. Ramakrishnan has explained how to installation of the R and data management and descriptive statistics and testing the normality and all. I think you all are thorough with that. And now we have another speaker, invited speaker, Dr. Akhilesh Kumar Gupta.
Good
He is
evening, sir.
working as
Good evening.
assistant professor, Department of Agricultural Statistics. Welcome, Dr. Akhilesh Gupta, Kumar Gupta.
Yes, sir.
And
Good evening, sir.
I'm so happy to see him. He did his master's program at Agricultural College Bapatla for his thesis work. And
Yes, sir.
now he is presently working as assistant professor in the Department of Agriculture, College of Agriculture, uh, OUAT, that is Bhubaneswar. He joined in the year 2021 after his MSc Masters in Agricultural Statistics, and during his PhD he got a selection, and he joined as a assistant professor at OEAT. He is doing his agricultural statistics doctoral program at Vishwabharati Shanti Niketan. His research and teaching experience includes statistical modeling, time series modeling, machine learning, and experimental designs. He has several papers in reputational and national and international journals in the area of statistical modeling, machine learning, regression, and designs. He has received silver medal at university level for excellent work during master's degree. I am welcoming once again to he's very good in R. That's why we requested him, and without his any hesitation, he accepted my request to deliver the second session. And during this time, he is going to explain the testing of hypothesis, chi-square test, and ANOVA correlation and regression. Of course, it is very short time, 1.5 hours, and we try to cover all these aspects. Now I request Mr. Akhilesh Kumar Gupta to start his session.
Thank you, sir. Thank you. Am I audible, sir?
Yes, yes.
Okay, sir. Uh, so, good evening to everyone. Shall I start my presentation?
Yes, yes.
Yes. So, we'll see a little bit of theory, very short theory regarding the hypothesis testing. Then we'll directly move to our R session. We'll more focus on hands-on session. So, a little bit of theory. I'm starting my presentation, sir.
Yes, yes. I am welcoming our organizing secretary, Dr. Muniswamy Garu, who is from Andhra University. He is a professor and head of the department. On behalf of him, I am taking to organize this, but he is busy with the next 2 days international conference. That's why I am taken and I am sharing his burden to organize this workshop. Welcoming, sir, Dr.
Yes,
Muniswamy
thank you, sir.
Garu.
Yes, thank you, sir. You are the entire workshop chair, sir.
Yeah, okay.
Yeah,
So thank you.
thank you.
Okay, right, thank you.
So,
Yes, it is visible.
yes, sir. Thank you, sir. So first, we will start with our hypothesis testing problem. That basically, in my topic, we have Z test, T test, F test, and chi-square test. So why we do hypothesis testing basically is to this is one picture that I want to share, that big picture of statistics. In statistics, basically, we have any problem about a population, and to solve that problem to or any question about the population, we gather the sample. So from the sample data, whether that question is answered or which how much certainty we can answer that question or solve the problem, that is basically the big picture of statistics, and that's why we have to do a certain hypothesis testing about the population. So when we take the sample from the population, we can do two types of analysis. One is descriptive statistics, and another one is inferential statistics. So this testing of hypothesis part is part of inferential statistics, where we will estimate a value from the sample, and we will check whether this estimated value is truly from the population or not. So that is basic understanding of hypothesis testing. So as our time is not much, we will not go into much of detail. We have two types of hypothesis: null hypothesis, which is basically uh, you can say pre-assumed conjuncture statement, which is tested until it is proven wrong or right. So that is our null hypothesis. And alternative hypothesis, you can say this is a research hypothesis. You want to test whether your means it is just the opposite of null hypothesis. So we have three types of alternative hypothesis. This is just for notation for mu. We have taken just for the understanding. We have taken the example of mean. So you can have three types of alternative hypothesis: two-sided, right-tailed, and right-sided or left-sided. Okay, this slide I want to explain a little bit. This is for population mean, like t-test and z-test we do for population testing, f-test we do for variance testing, and chi-square we do for categorical data. So this slide is basically dedicated to your mean testing, whether it may be one sample or two sample. So here we can see that we have two situations for testing the population mean. One is one sample, and second one is two sample. So and again, under one sample you will have two situations, whether you know the population standard deviation or you don't know the population standard deviation. So when we know the population standard deviation, we go for the z-test. When we don't know the population standard deviation, we go for the t-test. It is true for the both type of our condition, one sample and two sample. So in one sample, you will have basically one sample, and you will test whether the mean of that one sample uh, is equal to that an assumed value. That is assumed value, you can say it is equal to that population value. But when you have two sample, we check that whether the both means are equal or not in their population. We have two separate sample 1 and sample 2. So no, sample 2. So now we want to check whether these two means mu1 and mu2 in their population they are equal or not. That is the basic problem of hypothesis testing for two sample for mean. So if the population variances are known, we again apply z-test. If they are not known, we can have two situations. And one situation, if they are not known, we can assume both variances are equal, or we can assume both variances are not equal. So when we assume equal, we apply Fisher t-test. When we assume not equal, we apply Welch t-test. All these scenario we'll see in our R how we'll do this thing. And one last situation is there, that is your paired sample t-test. Paired sample t-test. Here, the difference between this paired sample t-test and these two tests is that here in paired sample t-test, the sample units are same. This is basically before and after experiment. Let's take an example like what is the heart rate right now you are sitting in comfortable position, and what will be the heart rate after a 100-meter sprint. So that will be a before and after situation. I will collect the data from the same unit before the 100-meter sprint and after the 100-meter sprint. So in that scenario we will have to use paired t-test. So in these two scenarios we have two independent sample, but in paired t-test we have the same unit for the two samples, same sample units. So this is the basic, you can say, population mean testing situation, where we have different types of scenario, different types of situation, and we will all see on a R how you will do this hypothesis testing. Someone was saying something.
No, you please continue.
Okay, thanks. Okay, so in between, like here I told that we have two sample and you can have two scenario, whether variances are known or unknown. So in that, at that time, we get the situation, we have to test the variance, whether the two, we get the situation of F test. These are the scenarios for t-test, and here in these two situation we have to test whether variances are equal or not. So we'll use the f-test to test that. If the f-test says that variances are equal, we will go for the Fisher t-test. If f-test says that variances are not equal, we will go for Welch t-test. So this is the basic understanding of population mean testing and population variance testing. Then another one is your chi-square test. Chi-square test, basically these two test, population mean, variance, these are for your quantitative data. You will have continuous quantitative data, like let's say height, weight, this type of data you will have continuous data. There you apply the mean test or variance test. But when you have categorical data, when you have frequency data, there you have to apply the chi-square test. We have three types of chi-square test. Here I have given two types: goodness of fit test and independence of attribute test. The formula is very simple for chi-square, but here obviously you don't have to use the formula. We will see how on hands-on we will do on R this chi-square test for goodness of fit and independence of attribute. So goodness of fit, basically use again in hypothesis testing, as I told, it is related to how your sample is performing with respect to your population. So we will have a population, a pre-assumed you can say ratio, and you want to see how your sample is, how good is your sample fitting to that ratio. That is goodness of fit. And independence of attribute, you may have two or more attribute, and you want to see those attributes are independent or not. One best example you can think of in this independent of attributes in this particular situation about the corona vaccination is one attribute, and getting the corona is second attribute. So we can check means one attribute, how many people have got the corona vaccination, and another attribute, of those people who have not got the vaccination, uh, how many got the corona, and of the people who have got the vaccination, how many got the corona. So these two attributes we can check whether they are independent or not. So these two means these three tests we'll see in R how we'll do hands-on. So sir, for hypothesis testing, should I move to R session?
Yes, yes, yes.
Okay, sir. Okay, so those who are joining in computer, I think they should focus more. So I have shared already these codes. I think everyone has these codes.
Yes, it was already shared.
Okay, participants, you can also answer, means if you have these codes. Okay, so we don't have, sir, someone is saying we don't have.
Already shared, but okay, we don't have because the organizers are already shared all these things. You do one thing, we will share later. Otherwise, you can explain step by step so that they can understand, and we'll share the code later.
Okay, sir, okay.
Because these are being organized by from Andhra University.
Okay, sir, okay, okay.
Right, right.
Okay. So first we'll see the jet test, one sample jet test. How? So as I told, when you know the variance, you have to apply the jet test. Okay. So when you apply, there is no inbuilt command for jet test, but there is one package called BSDA. So like sir told in morning session, you have been explained how to install the packages and all. So I will assume that you know how to install package and how to load the package. So for jet test, you will have to get a package called BSDA, and you will get into your library. Then you will able to perform jet test. So I have taken the example of height data. This is one height data, just a general entry of the data as a vector. I did vector entry of the data, and I got height variable. So this is my height variable. I have got around 9 data points. Yes, I have got nine sample size 9. So this you can apply the jet test directly, jet dot test, and you have to give the variable. I recommend everyone to use this help command. This Yes, here in this help, you can get everything how to use the code. You don't have to remember anything. You don't have to like write anything on pen or paper. You can get into the help and you can see how you have to use the function. This function is based on standard normal distribution. It is already given, and how you will have to give the argument, y argument, mu value, sigma x value. So these are the
Sir, your
simple
voice is not audible, sir.
Sir, please increase the font size.
font size. Now it is
Sir,
okay.
please increase, maximize the screen.
It is maximized. Is it not visible?
Yes, sir, it is not visible.
Not at all visible, sir.
It is
Visible,
visible,
but
sir, but
very
Is the size of
it's
font,
very
sir?
too small, sir.
Can maximize our screens.
R is this is full screen. Means sir told about R studio or R.
Yeah, this only.
font.
This one, sir, it is visible.
Yeah,
I
it is
think it is
visible, but you can double click so that it will go up to 100%.
Sir, every participant can zoom their
Yeah,
themselves,
yeah,
sir.
that is
Yes,
there.
sir.
No, sir. No issue from your side, sir. You can continue, sir.
Yes, sir. I think sir means it is.
Yes, it is visible, Akhilesh. You please continue because the participants can, on their own systems, they can zoom it. They have the option.
Yes,
Okay.
sir.
Please
So
continue.
yes, sir. So, like I told, you can use the help function where you have to give your argument x value, mu value, sigma x value. So, like you can see here, I have given the z test and I have given my variable, which variable I want to test with my mu value. So this is the, you can say these are the way of writing the code in R. This has means you have written just a comment. This is not a code. It will not be executed. So here I have given the information. I'm doing the one sample jet test, and this is my mu naught value, my assumed value 1.5, and this is my sigma value, my standard deviation. So same thing I have given in these arguments, and this is alternative. Like I told, we have three types of alternative: two-sided, right-sided, and left-sided. So in this example, I have taken two-sided. I have taken all three one by one. So first we have taken two-sided, then I have in 1.5, then my sigma x value and confidence interval. Sorry, confidence level, like we do at 5% level of significance, that is your level of significance. But if you say confidence level, that will be your 95. So I have taken 0.95. You run this command and you will get the result one sample z test. So here it is giving your test statistic value z equal to 2. Here it is giving p value. Here it is giving confidence interval of your mean value, and this is the mean value. So this is the mean of this height, and you are getting whatever the things you require in your hypothesis testing problem, everything you are getting from confidence interval to test statistic value to p value. Now, how you interpret p-value? If it is less than 0.05, your test is significant. If your alpha is 0.05, so it should basically p-value less than alpha, your test is significant. Otherwise, it is not significant. Then similarly for right tail test, right sided test, we change the alternative from two sided to greater, and you will get the p value, different p value. It is basically half of this p value 0.02275, half of 0.0455. Then again similar things, and you can check also for less than. So again p value changes. So this is how you can do one sample z test. If you have two sample z test, you can just put x and y both in these argument, and you will have to put sigma x as well as sigma y. Then you will get two sample z test. I have not given here. You can check yourself. Then I come to one sample t test. This portion, one sample t test, student t test, basically what we call. So one sample t test, that means we don't know the sigma value. We don't know the population standard deviation. So we have the height argument and we have the assumed mean value that we have to give. Similar type of argument, you can see that height, mu value, alternative, and confidence level. You don't have to give sigma here because sigma is unknown. So you will run this command and you will get the one sample t-test result. You are getting here test statistic value, you are getting your degrees of freedom, you are getting your p-value, you are again getting your confidence interval. Many times confidence interval is required and it is a little bit difficult to calculate than doing the hypothesis testing problem. So you are getting both things in one command. You don't have to calculate it separately. So these are the things you can get from your one sample t-test. Just t-test is, it is a very, you can say, basic command, and it is very powerful command. This is the only command you require for any type of mean testing. This is the only command you require for any type of these all four type of you can say sigma unknown situation. You only require t-test. I will show you one by one how you can use this command for all type of situation. Okay, so this one was for our two-sided. Then we can again go for right-sided, and we can go for left-sided. Okay. Now this was one for one sample. Now we come to two sample t-test. So this is command for how you enter your data. In morning, which methods are told for data entry? Can anyone tell me?
Yeah, read CSV was used.
Okay, sir. Okay, okay. So read CSV was used. Okay. So this is in when I explain, this is the most easy command. When I can say read CSV, then this file dot choose. There are many methods. You can give your path of the file here. You can give clipboard here, but this is the, in my opinion, best command to do the data entry. It will open a prompt in your computer and you can select your file from there, just basic computer thing. So you will run this command and you will get a prompt. I think it is a little bit taking late for me. Just a minute. Okay, so I run this command, I got this type of prompt. You will also get this type of prompt in your system, and you can select your file from your system itself. So here I have my file. So this is my marks data. So all these commands and file I have already provided. You can get this from the organizers. So you will open this and your data is entered. You don't have to do any type of file path or something like that. You just run this command. You will get a just computer prompt and you can select your file like you do when you upload any file or you save any file, simple type of thing. So you can see the data. This is basically we have marks data for new method of teaching, and this is existing method of teaching. That type of data I have given, and we teaching method are different or not in respect of marks of the students. So these are marks of a student with new teaching method. This is the marks of a student for existing teaching method. So like I told, for performing the t-test, first you will have to know whether the variances are equal or not for the t scenarios. So first we'll perform whether our variances are equal or not. This is our f test. Okay. So for the f test, you have very simple command var.test, variant.test. So first I have taken my marks new data, then marks existing data. This dollar is basically to extract you can say one variable from a data frame. This marks is our data frame, and I have extracted new from that data frame and existing from that one data frame. Again, I will show you the help of variance.test. See, perform an F test to compare the variances of two samples from the normal population. So you have to give your X and you have to give your Y, and whatever the things you want to give. If you don't want to give, leave it as default. It will take the default thing and it will give you the result. You don't have to worry about it. So here I have just given the two variables, my X variable and Y variable. I run the command and I got f test to compare two variances. This is my test statistic value, my numerator degree of freedom, my denominator degree of freedom. Like here you can see there are 10 observations. So I got numerator degree of freedom 9, and in denominator second variable I have 12 observations. So I got denominator degree of freedom 11 and p value. So from this p value you can see that it is greater than 0.05. I will say that both not equal. Sorry, both variances are equal. Both variances are equal. So perform t-test as per the result from the f-test. Here variances are equal. If the p-value less than 0.05, you will say that variances are not equal, and accordingly you will modify the your command. So now I will show you how you can do the same thing from the t-test command. So here you can see there is an argument variance dot equal. So if the variances are equal, you will have to write here true. If the variances are not equal, by default it is false. Okay. So if the variances are equal, you will have to modify this argument. So here you can see that I have given the t-test command my x value, my y value, my alternative. I want two-sided test, and I have given the argument variance dot equal to t. Instead of writing complete true in capital, you can also write capital T for true and capital F for false. So there is means it will accepted as true and false. So I have written capital variance dot equal to true because my F test given my both variances are equal. So I run this command and I got two sample t test. So same thing, you got the test statistic value, you got your degrees of freedom, which is n1 plus n2 minus 2 here. Here I have written degrees of freedom n1 plus n2 minus 2. So 10 plus 12 minus 2, 20. Then p value you got the confidence interval of difference between means and mean of x, mean of y. So here again you can see that p value is less than greater than 0.05. You can say that both methods are equal, means there is no difference between the two means of sample x and sample y. So this is how you perform two sample t-test when variances are equal. If the variances are not equal, you can simply change this true to false. We will see that we have again a data set, shrinkage data. I will enter this shrinkage data. Okay, so you can see that we have two variables, lower and upper. I want to test whether these two mean of these two populations are equal or not. So again, I follow the process. I will check whether variances are equal or not. So here you can see that p value is less than 0.05. So now I will say that variances are unequal, and I will modify my code accordingly. Here I have written my x value shrinkage lower variable, shrinkage upper variable, alternative two-sided, and variances are variance equal to false. That means variances are not equal. So if the variances are not equal, I will run this command, and here you can see that it is giving Welch to sample t-test. Like I have written here, it is Welch t-test. First one is Fisher t-test. So here it is performing Welch t-test, and the difference is degrees of freedom. Your t-test is means you are getting the test statistic, you are getting the degrees of freedom, you are getting the p-value. So here p-value is less than 0.05. You can say that both means are significantly different. So many a times student do this type of mistake that they don't check the variance before doing the t-test. So it is very important to check the variance whether they are equal or not, then perform t-test accordingly on the basis of whether variance is true, equal to true, and variance equal to false. That's how you have to do it. So I think all this, then paired t-test. For paired t-test I have not taken the example, but it is very easy. You have to give your before sample x and after, sorry, before experiment x, after experiment y, and here there is an argument pair equal to false. You just have to change it into paired equal to true. It will perform paired t-test. The main thing is you have to understand in paired t-test that your both the samples will be equal size. Here you have two different sample size, uh, different sample sizes, but for paired sample you will have to have both samples of equal size, and you will change this uh, paired argument equal to true, and you will get the paired t-test, your paired t-test result from the same command, t-test command. You will get the paired t-test result. So I think this is how you can do your F test and T test and Z test. Z, T, and F all. It is very easy in actually in R. Means you just have to have three commands. One is Z test, one is T test, and one is variance dot test. All three simple commands, you can complete your hypothesis testing of mean and variance. Sir, should I move to chi-square test?
Yes, yes.
Okay. So I have taken two examples of chi-square test, a test for goodness of fit and test for independence of attributes. So test for goodness of fit, as I told, you will have some type of expected frequency, and you will have to check whether those your observed frequencies are good fit with those expected frequencies or not. So I have taken here a blood group example. Again, I will enter the data and I will have the blood data. Okay. So here you can see that we have four types of phenotype. We have four type of blood group A, B, AB, and O, and these are my observed frequencies. I have from the total I have 89% who have A blood group, 18% B blood group, 12% AB, and 81 O blood group, and these are my expected. You can say probability. Sir, my screen.
Can you please share again?
Okay.
Yes, okay. Now we got it.
Okay, sir. Okay. So these are my expected probabilities that what is the probability of expected probability of getting A phenotype, what is expected probability of getting B phenotype. So these are my expected probabilities. So these are the things you require when you do chi-square test. Okay. So again, I will recommend you to use this help function very frequently. You will get everything from here. So chi-square.test, it performs chi-square contingency test and goodness of fit test. So later on we will see contingency one, and right now we are seeing the goodness of fit. So here you can see that we have to give x value, that is our, this is our x, means you can see it is everything, it is given here. You don't have to means, as I told you, don't have to remember it, you don't have to take the notes, everything is it is given. So it is a numeric vector or a matrix. You can directly give it as a matrix when you do goodness of fit test, we will see later on, but here you can give a numeric vector. So this will be our numeric vector value. And for the expected frequency calculation, you will have to give p value. P means probability value. Okay, so by default it is given here, but here we have our expected probabilities. So we will give these two vectors into our command, and we will perform the t-test. Oh, sorry, chi-square test. So as you can see this here, chi-square test, I have taken blood data, and from that blood data I have taken persons. So this is my blood data, and I have taken persons as my x variable, and in place of p equal to, I have taken blood data and expected probability. So from the blood I have taken expected probability as the P, and correct equal to false. This is your Yates correction. If you know the theory about chi-square, there is one thing called Yates correction for continuity. So here we don't have to apply any type of Yates correction because our observed frequency is not less than 5. So I have taken correct equal to false. If you have to do the Yates correction, you do it is equal to true. See, here it is written correct, a logical indicating whether to apply continuity correction or not. So you can check whether you want to do continuity correction or not. So I don't want to do it here, so I have taken correct equal to false. I will run this command, and you will get a chi-square test for given probability. You have given this probability, you got the chi-square value, you got the degrees of freedom, and you got the p-value. Here p-value is again greater than 0.05. So here the null hypothesis and alternative hypothesis you will have to understand. So null hypothesis will be that your observed frequencies are good fit with your expected frequencies, and alternative will be your observed frequencies are not good fit with your expected frequencies. So when we have our p-value greater than 0.05, you will say that it is the good fit with your expected frequencies. So that's how you can interpret this p-value, and your test statistic value. You just have to report that, and p-value, whether if it is less than 0.05, you will say that the observed frequencies are deviating from my expected frequencies. So that is the basic interpretation of chi-square goodness of fit. So then we come to our second type of chi-square test, that is independence of attributes. So here I have taken flu data. Like I told, see, example of independence of attribute for vaccine and incidence of flu. Incidence of flu. So it is very similar to your corona. We will see the data, and we will get the idea what the data I have taken. Here it is flu data, and you can see that. See, so this is our one attribute with no vaccine, one shot and two shot, and this is second attribute whether the person got the flu and whether the person got no flu. So this is the basic data, and we have to test whether these two attribute, vaccination and getting the flu, is independent or not. Okay. So like I told, in chi-square you can give your vector as well as matrix. So here in this command for independence of attribute, I have given the data in matrix form. So this is one type of writing the code. This is means right now I will not be able to explain because of time. This is how we write our index. You can see the flu data. This is your flu data, and I want to remove my column. So I have before the comma you give the index of row, and after the comma you give the index of column. So I have taken the comma, and before the comma I have left everything. So I want to take all the rows, and I have written -1. So I will remove the first column. So it will take this much of data set from this flu data. And again I will do correct equal to false, and it will give you the Pearson chi-square test for independence of attribute. This is your chi-square, and this is your p-value. Here you can see that it is less than 0.05. So here again the null hypothesis and alternative hypothesis you will have to understand. The null hypothesis will be the attributes are independent, and alternative hypothesis will be attributes are not independent. So when the p-value less than 0.05, you say that these two attributes, vaccination and getting the flu, is not independent. That means they are affecting each other. So that's how you can interpret to this independence of attribute chi-square test. So sir, hypothesis testing, I think we have completed.
Yes, yes, okay. Now we can go for ANOVA.
Sir, ANOVA or regression correlation?
Yeah, whatever it may be,
Okay,
because even testing of hypothesis ANOVA also right.
okay, okay. So first I will see correlation regression, then we will go to ANOVA. Okay. Okay. So a very short description about the correlation. We all know it is a statistical measure between a statistical measure to describe the strength and direction of linear relationship between two quantitative variables. So here two things we have to remember that for calculating the correlation, your both variables have to be quantitative, and it gives the linear relationship. If any other type of relationship is there, curvilinear, quadratic, cubic, it does not consider those type of relationship. You cannot measure this curvilinear relationship with correlation coefficient. It has to be linear relationship, and it will give you two things: strength and direction. Strength means whether it is positively correlated, highly correlated, weak correlated, moderate correlated, and the direction, positive or negative. So these basic type of information you will get from the correlation coefficient or correlation study. So there are two methods of studying the correlation. First one, this is, you can say, indicative method. By plotting a scatter plot, we plot x and y against each other, and we'll get the idea what is the relationship between two variables. So by seeing these plots, you can understand this is a strong positive correlation, weak positive. The data points are not very dense. Here data points are very dense, and data points are on in one line, so it is very perfect positive correlation. So similarly, for negative, strong negative, weak negative, and perfect negative. So these scatter plots gives you the idea which type of relationship you are getting, but you will not get any quantitative value like correlation coefficient. So we'll have to study two types of correlation coefficients: Karl Pearson coefficient of correlation and Spearman's rank correlation. And one more thing is there, non-parametric Kendall's tau. Again, we'll see in R how you can calculate. So we'll see how both these coefficient you can calculate one by one in R. So first you'll see Karl Pearson, Spearman, and Kendall's tau. And one furthermore topic is the regression. Like in correlation, we just study the relationship between two variables. What is the relationship, whether it is positive or negative, strong or moderate or weak. But in regression, we study what is the exact relationship, how y variable is changing with the change in x variable. So as I told, in regression and correlation, we have two variable, x and y. Y is generally in told dependent variable, x independent variable. So in regression, we get the exact relationship between x and y. How y variable is changing with the change in x variable, that we get to know when we study the regression. So when we have two types of regression, simple linear regression and multiple linear regression. Simple means you have only one independent variable, only one x variable with one response variable will be always one dependent variable, and you will have only one independent variable in simple linear regression. So you will study how your y variable is changing with the change in x variable. And these are the theoretical formula how you calculate regression of y on x. Theory will not go much. And multiple linear regression, you have more than one independent variable uh, against a dependent variable. So here you can see x1, x2 till xk, you can have any number of independent variable. So this is multiple linear regression, and we want to know what is the effect of x1 on y, x2 on y, x3 on y, whether their effect is significant or not. So all these problems we'll see. If they are significant, we have to keep them on the model. If they are not significant, we have to remove them from the model. So all these problems we will explore in R, how you can do it easily. And this is again the ANOVA of multiple linear regression. Then this is one important thing, how to know whether your regression model is good or not. So we have certain measures to check whether your regression model is good or not. So one is goodness of fit R square, simple R square, then adjusted R square. We'll understand when we get the result, we'll understand what is the difference. Basically, this adjusted R square penalizes you for the non-significant variables. If you add some variable which are not contributing significantly to your model, then it will penalize you, and it will means indicate that this model is not good for means to be included in the this variable is not good to be included in the model. That's how it works. R square and adjusted R square. Okay. Then there are some assumptions of linear regression. We have in regression, linear regression, and as well as in ANOVA, we have similar type of assumption of linear relationship, homoscedasticity, normality of error, multicollinearity, and autocorrelation, independence of observations. So we can check them by plots and as well as some you can say formal test, but most you can say common thing to check the assumption is to by plotting. So we'll see how you can use the different plots. I have written already here which plots we will be using to check these assumptions. Plot residual versus fitted values, residual versus fitted values, QQ plot, VIF factor, again residual versus fitted values. So these are some plots we'll see to how you can check your assumptions. If any of the assumptions are violated, how you can what you can say rectify them, we'll see. Then there is again one problem in multiple linear regression to select the variables. If there are various means numerous variable, more than 2 variables, it is not necessary that all the variables are significant, all the variables are contributing significantly to your y variable. So some of the variable you will have to keep, some of the variable you will have to remove. So there are 4 methods to do it. This one is the most important stepwise regression method. We will see how you can do it, how you can select the variables to keep in your model. Okay, so we'll go to our session and we'll do it one by one. So first we'll complete the correlation, then we will see simple linear regression, then we'll see multiple linear regression, variable selection, final model. And this is one of the important thing that I wanted to tell. If time permits, I will tell. Okay, so we'll start our session. I have given this PRD data. When you get the data in command, you can check by yourself. We have the PRD data. To clear the console, you can use this this icon, or you can use Control plus L. If you want to clear this console, whatever, see, clearing the console does not mean whatever you have done, it is vanished. The variables are already saved, it is saved there in your console, but whatever it is written here, it is cleared. Okay, so I will see my PRD data. I have 6 variable, one is y and other 5 are my independent variable. So we'll see how the y variable is related to our different independent variables. This is one command structure. It is very important to know the idea about your data. Means if you don't know anything about your data, you can use this structure command str and you can get an idea that it is a data frame which have 6 variable, each have 29 observation, which type of variable you have. All these variables are numeric variable. If any of them is you can say qualitative variable, it will be written something different. You can get the idea of about your data from the here. Okay. So it is very, you can say, important command to get the idea about your data. Okay, so like I told, for correlation study, first we will see a scatter plot, then we will see the correlation coefficient. So this is how you can, I have given 2 commands to plot your scatter plot. This type of thing is called formula, you can say formula method, and this is you are giving x and y variables separately. So formula like formula, just say key. Okay, here we have written y equal to b naught plus b1 x. So here you are writing by basically your y is dependent on x. So in coding language we write it like this: y is dependent on x1, or y is dependent on x2, y is dependent on x1 plus x2. in multiple, we have written y equal to b0 plus b1 x1 plus b2 x2. So in command you will write y tilde x1 plus x2. This is how we write formula in coding, how we write in R. So this is I have written for plotting y is dependent on x1, and I have to take the data points from where I will get the y and x value. I will get the y and x value from my PRD. So I have given data equal to PRD, and these things are means a little bit detail. You will have to go on graphics of R. You will get some idea. You check first when you do it continuously, you will get the idea. This is point character. There are various point character in R. You will get it, and this is the color of point. What the color I want to get to the points. Okay, so there are, I think, more than 600 colors option in R, and I think 25 character option in R for your plotting. Okay, see here you can see that these are the point character. If I have given 19, I will be given this type of points. If I give 12, I will be given this type of points. If I give 25, my points will be shown like this. So these are the point characters. You can choose any of them as per your choice. And point color, as I told, there are various color options. Here I have 657 colors. You can choose any of the color option from these 657. I have taken very means you can say simple red color. So I will run this command and I will get a plot like this, his scatter plot. So this is my scatter plot. You can see that from this plot I get an idea there is positive, you can say moderate type of positive relationship between y and x. So if you write like this, y followed by x, y will be plotted on vertical axis, x will be plotted on horizontal axis. If you use the second command, you will again get the same type of plot, but here if you are using the variable method, you can say you are giving the two variables one by one, x1 and x variable and y variable. Then you will have to give the x variable first, then y variable. If you are giving the formula one, you will have to write y followed by x. But if you are giving the x and y thing, then you will have to write first x, then y. Okay. So I will run this command, and again I am getting the same type of plot, but here it is changed. PRD $x1, PRD $y. You are getting the same plot. So you can use either method. Then here we have this command which will plot each of the variable against each. Like here in PRD we have 6 variables. So each of the variable will be plotted means against each of other variable. So if I run the command, you will get this type of plot. So when you understand, if you want to understand the data completely, if by one plot, you can see this type of plot. So this is y versus x1, this is y versus x2, this is y versus x3, y versus x4, and this is y versus x5. So here you can see that there is a linear relationship between y and x1. There is almost no relationship between y and x2. Similar thing here. Here there is negative relationship. Here there is curvilinear relationship. So this type of plot you can get from the plot command. This plot command is very, you can say, a high level and very powerful command in R. It serves so many purpose. You get into R, you'll get the idea how powerful it is. So, and this plot is basically your relationship between x1 and x2. This is plot between x1 and x3. So like this you can get the idea about every relationship between every relationship among each other. So that's how you can do it here. Now after scatter plot, as I told, we have to calculate the correlation coefficient. So there is very simple command COR to get the correlation. There is no difference between correlation between x and y and x, so you can write any one first, y or x. There is no problem in correlation. In regression there is a difference, but in correlation there is no difference. So I will run this command and I will get the just correlation value. There is 0.6276 correlation coefficient between y and x1. This is your Karl Pearson coefficient. If you do not specify anything, it will give you the Karl Pearson coefficient. And if you do not specify any variable from a data frame, it will give you the correlation matrix. Most people want a correlation matrix, correlation among each of the variable. So you can see y to x5 on the row, y to x5 on the column, and this is how you get the correlation. So correlation between y and y, obviously 1. Correlation between y and x1, same thing we got here. And correlation between y and x2, y and x3, like this you're getting. So see, the plot we got, like I told, there is almost no relationship between y and x2. So we are getting 0.10, very weak relationship. Then again with x3, same thing. Then with x4, we have very strong negative relationship. And here it is, if you see it linearly, it is negative, but it is curvilinear relationship. That's why it is not means high. It is very weak negative. You can see that. So you can get the idea. You can get the exact value from your commands CUR. So plot for plotting, CUR for correlation. And if you want to get some other correlation value from other method, you will have to specify. Again, how you know that there is any other option, you go to your help and you can see that here there is method correlation. You have 3 methods: Pearson, Kendall and Spearman. You can specify any of them and you will get the correlation value by that method. So I have given one by one all 3 correlation. This is by Carl Pearson, this is by Kendall's method, and this is by Spearman's method. So you can see all 3 are giving different type of correlation: 0.6276, 0.384, 0.527. So any of the method you want, you can get the correlation value. Then we have to test the correlation, whether the correlation is significant or not. Okay, so there is very simple command core.test, but the demerit of this command is you will get to test one by one. You cannot test all of the correlation at once. For that we have separate package and command. First we'll see how you will test one correlation. Like here we find one correlation value, we want to test whether this is significant or not. So for that you will have to use core.test. So correlation value is tested by t-test. In theory, we also know, I think. So we are getting the test statistic value, degrees of freedom, n minus 2, and p-value. Here your p-value is less than 0.05. So obviously it is significant. And you are getting your confidence interval and your correlation coefficient. So all these things you are getting Pearson product moment correlation by correlation.test. So this is how you test your correlation value. But now you want that I have correlation matrix by Carl Pearson, and I want to know whether all these correlations are significant or not. Okay, I don't want to test one by one, y with x1, y with x2, or x1 with x2, x3, like that. You want to test each correlation at once. So for that you will have to install this package hmisc and bring it into your library. Okay, so if you install a package, this step is must. If you don't do it, your command will not work. Okay, so library is very important. Now there is command rcore. Okay, so this will provide the correlation coefficient value and their respective p values. It will not give you the t value, just a statistic value, but it will give you the p values. So I run this command and I will get the correlation values and my p values. So you can see that the correlation between y and x1 is 0.63 and its p value is 0.003. You can verify it from here. So my correlation is 0.63, 0.627. So basically it is 0.63 and it is 0.003. 26 means it is 0.003. So my p value is 0.003. So you are getting the correlation values and you are getting the p values. So this is how you can test it. All the correlation at once. Okay. So you can see that it is 0.85, its p-value very less, less than 0.05, it is less than 0.05. So you see the correlation value and its p-values. Those correlation which have p-value less than 0.05, they are significant. Okay, so correlation completed. We get to regression. First, we'll see simple linear regression. So we have PRD data. We have PRD data, and we want to fit. First, we want to fit simple linear regression. We want to fit y on x. So we'll do y on x. See, for regression, this LM is very means powerful command. Again, I want to tell LM means linear models. You want to fit any type of linear model, LM is your command. So LM means fit your linear models, simple linear regression, multiple linear regression. Even the ANOVA it can also fit, but we use a little bit of different variation. But LM is your command for linear models. So here I have given, you will see various, you can say, variation of this type of command like directly PRD dollar. You can write this command like this also, PRD dollar $y followed by PRD dollar $x1. But I will suggest you to use this type of format, a formula format with data. See this one, formula then data. I will suggest you to do this thing because it is important when you do forecast prediction or something like that. It is important to do like this. If you do any other type of variation, it will be difficult to do a prediction and you will not be able to understand where is the error. Okay, so whatever it is given, first we will give the formula, then we will give the data from where we will get the y and x1. So here we have given y followed by x1 and we have given the data we are getting from the PRD. So I will fit the model, and to get the result about your linear regression, you will have to use the summary command. So I have given summary of fit 1 and it will give you so many information. So this is your beta values. This is intercept beta values. This is descriptive statistics about residual, which is means not required now, but later on we can see something like how we can use them. But important thing start from here, from the coefficients. So this is your beta naught value, This is your beta 1 value, like we have here regression model. Okay, this is beta 1, beta naught and beta 1. So this is your beta naught value, this is your beta 1 value, and simultaneously you are getting whether those coefficients are significant or not. So you are getting standard error, you are getting t value, and you are getting p value. So p value less than 0.05, you can say that x1 is significantly contributing to your y. So this summary command is again very powerful, helpful command. In most of various things you can get from the summary. Then this portion gives you a idea about your R square value, your significance of regression or not. So you are getting your residual standard error. Residual standard error basically, when if you understand the ANOVA, it is a root of this value. Standard error, this is your MSE or EMS, and you get the root, you will get the standard error value. So this is your residual standard error. Then this is your R square, like I told, we have two things, R square and adjusted R square. So we have R square 0.39 and we have adjusted R square 0.37. Your adjusted R square will be always less than multiple R square. And that is, you have to remember it will be always less than R square. Then you get the F statistic, this F value, and again its P value also, whether F is, whether your regression, overall regression is significant or not. These T values give you the significance of coefficient. When we go to multiple linear regression, you have more than one independent variable. So these coefficient, these P values will give you the significance of individual coefficient. But this F statistic, these things will give you the idea whether your overall regression is significant or not. So that's how it is important, these p values and this p value. That's how it is different. We'll see in multiple linear regression how what I'm trying to explain. Okay. Then you can get the confidence interval of your these two coefficients, beta naught and beta 1, by this command. These two, you can say limits, lower limit and upper limit, 95% confidence limit. Then you can plot your regression line again I have plot y followed by x. I given the data, and these three things are your, you can say, graphical things. You give the main, what is the heading of your plot, and x, what is the label of your x-axis, what is label of your y-axis. So this is, you can check like this: regression of y on x1. Whatever I have written here in double quote, it will be given my title. Whatever I given on y lab, it will be given on y axis, then x axis, and you will get your scatter plot. Then I want to fit this line. You have seen many times there is regression plot, your scatter plot. Over that regression plot, you have your regression line. So for that, our command is AB line. You have to give your fitted model into the AB line, and you have to specify the color, which color you want. So I want my blue color, and this is my regression line. So this is how you can plot your regression line on in R. And in many people compare Excel with R, that we want our regression line and R square written on my graph. So you can write with this text commands. So this is my text command. This is the position I want to specify. What is my x coordinate, what is my y coordinate, and what I want to write. So you will have to write within the labels, double quote, my regression equation. This is my regression equation: y equal to 113.75 plus 0.18 x1. I want to write this one in blue color, and I also want to write r square in blue color. So I will run both these commands, and I have written here. You can adjust a little bit your coordinates, so it will be, means what I can do here. I think I have zoomed it, that's why it is looking like that. Now it is okay. Y my regression and my r square value. So I think it is done here. Simple linear regression. And these are the plots you can use to you can say, check the assumption of your regression. This is residual versus fitted plot. I will give you a link or file where you can read about this thoroughly. I think I don't have much of time, 20 minutes left, so I will move to multiple linear regression. You can check in internet also. There are various description about these plots, how you can check your assumption through these plots. These are very important plots. So let's move to multiple linear regression. In multiple linear regression, we have more than 2 independent variables. So here we have written like here y equal to beta naught plus beta 1 x1 beta 2 x2, like this. Here we have to write y followed by x1 x2 x3 x4 x5, like this, and we have to give the data. So we fit the data, and we get all the result about all the variables. So this is your beta naught and beta 1, beta 2, beta 3, beta 4, beta 5, and their significance, whether it is significant or not. So when it is less than 0.05, it is significant. When it is greater than 0.05, it is not significant. So here you can see that multiple r square, adjusted r square, f value, p value, everything similar. Now I told you the problem of variable selection. You want to select the variable. See, all these variables are not significant, so it is not very simple to say that it is not significant, we remove this variable. There are some different types of algorithm that work behind the scene, that you by seeing only this table, you cannot say that this is not significant, I remove this and I will fit with 4. There are as I told, we have 4 methods: all possible regression, backward elimination, forward selection, and stepwise. So these methods are used to see which variable is actually significant and which variable you should remove. So these this action you can do by this package OLSRR. You will have to install this package. I think, okay, I have the package OLSRR. You can install the package and get into library, and you can see I have written OLS step all possible. First method, all possible method, then backward elimination, forward selection, and stepwise. We'll see the stepwise. You can check all of these one by one. So this is the result of stepwise. So here you can see all the candidate terms, 5 candidate terms. In first one, they have added the 4th variable x4 and got the model intercept plus x4. Then in second step, they have added the 3rd variable x3. Then they got the model and everything related to that model, then no more variables to be added or to removed. Okay, stepwise means you can add the variable and you can also remove the variable. So here we don't have to remove anything else. So now our final model is x3 and x4. I only want to include x3 and x4 variable in my model. Rest of the variables I want to remove. Okay. So you can see that with only x3 and x4, my r square is 86%. And we have, when we have all the 5 variables, my r square was 90%. So almost only 4% of difference for 3 variables. So that is not significant. You only have to include your significant variables. So by this command, you can get which variable you should take into your model and which variable you should remove from your model. Here you can specify at which level of significance you want, whether you want to take it 5% or you want to take it 10%, you can specify here. P ent means entry of the variable, P remove is removal of the variable. Again, I told you check the help command, you will get the everything. You use the Google, you use the help, everything is there. Then this is our VIF for multicollinearity. VIF factor, if it is around, you can say 4 or 5, it is, you can say warning to see whether it is actually related to some other variable or not. If it is around, you can say thumb rule around 4, less than 4, you are safe. So here we have one variable x5 which is showing VIF value 5. You should consider checking it whether it is actually correlated to something, or what is the reason behind it is getting VIF 5. Then you can also get your AIC and BIC values. These are model diagnostic values. Lesser it is, better it is. So our final model is y followed by x3 and x4. We got the our analysis and got the result. Then AIC, and here you can see VIF value close to 1. So if it is close to 1, there is no multicollinearity, right? So this is our very good model. We got the final model. This R square is good, adjusted R square is good, VIF is good, no problem. Okay. So sir, correlation regression completed, sir.
Yes, yes, Akhilesh, okay.
Okay. So sir, design.
Minutes time is there, yes, we can, yeah, give ANOVA.
Okay, sir.
He has more than 2 treatments.
Okay, sir. Okay. So for ANOVA, we'll see CRD, RBD, factorial, or something specific, sir, should I tell, or we start from CRD?
No, here it is a heterogeneous group. I think it is better to start from CRD.
Okay.
And when you have already shared the coding, I think they may practice the remaining. Huh?
Okay, sir. Okay.
When time permits, right?
Okay. So we'll start with CRD. I have given plant character data, one plant character data. You should see that. So I have plant character data here. You can see the plant character data. Here we have treatment, replication, and 4 variables: year head per plant, year length, grain weight, and this is grain yield, I think. Grain yield, yes. So this is my grain yield. Okay. Grain yield data. So this is our dependent variable, basically grain yield data, and we want to check whether our treatment are significantly contributing to the grain yield or not. So that is
phone
basically.
net balance ఉందా నెట్ ఇది అయిపోతుంది.
Please mute. Okay. So this step I want to make very clear. This step is very important where when you are doing your design analysis in R. Okay. You have to understand what are your factors and declare them as factor. Let me plant character. Okay. So in design, your treatment, replication, dependent variable, your y variable, everything is else is almost factor. Okay. So first you see the structure of this data. Your structure of this data, it is showing your character data, treatment, it is showing your replication character data, all other variables, numeric data. Now, this treatment and replication are my factors. My treatment is one factor, replication is my second factor. First, I will have to declare them as factor by this command. You can see the command by yourself. You can see how but this is very important. You have to declare them as factor. So I declare my treatment as factor and replication as my factor. Now I check my structure and you'll see the difference here. See, now first it was character variable, now it is a factor variable. The difference is here the character variable, all your T1 are different. Your T1, one observation, T1 again, it is second observation. But when you declare them as factor, those are one label. T1 is your one label, T2 is your second label, like that. So you can see here T1, 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 but here it is saying T1, T2, T3, like that. So similarly for the replication, R1, R2, R3, here it is R1, R2, R3, it is given like that. So that's why it is showing like that. But declaring them as factor is very important. Otherwise, you will not get the correct result. You will get the regression result, and you will be means the results will be very misleading. So it is very important declaring them as factor. So here it is very like I told in your linear model regression, it is similar to your linear models, just the command is different, AOV. Everything else is simple. There we have given LM, our Y variable, our X variable, and our data. Here we are using the AOV command, our Y variable, X variable, and our data. So here our Y variable is grain yield, our X variable is treatment, and our data is plant character. And our command is AOV, analysis of variance. So I run the command, again I use the summary. You will get the ANOVA table. This is very basic CRD ANOVA table treatment. You'll get the degrees of
ప్రాబ్లం
freedom.
ఎందుకు వస్తుంది డోర్లో వెళ్ళదా
And you will get the degrees of freedom for residue of square, mean sum of square, F value, P value. P value less than 0.05, you can say that your treatments are significantly affecting the dependent variable. Then again ANOVA will also give you an ANOVA table, but same results you will get, but a little bit minor difference. I think there is no difference, but again you can use any of these commands. Analysis of variance table, same thing you will get also by ANOVA. So this is basic ANOVA. Now the main thing is how you will do your what I can say, multiple comparison. For that, yes, one more thing I need to tell. For any type of design analysis, ANOVA analysis, this AgriColi package is very important. Library AgriColi. Okay, this package is very important. First you load this package, install this package, then only you go for any type of design analysis, any type of ANOVA analysis. Otherwise you cannot do anything. Okay, so now we got our treatments are significant, so we want to check which of the treatment is significantly different from the other treatment. Pairwise comparison basically. So we can do pairwise comparison by three methods: LSD, least significant difference, Duncan test, and by Tukey HST, honest significant difference. I will go one by one, all three. Again, in LSD test, you can see everything through this help. I will just show once LSD dot test. Here you have to give your Y or and Y. It can Y. What is the argument? Model. You can give your model whatever you have fitted from the ANOVA or LM and or your Y variable. So you can give either this fitted model fitted.crd or you can give this grain yield Y also. So it is better to give model in CRD, RBD till where it works. In some type of design, factorial and some higher design, it does not work like that. You have to give your Y variable, but where it works, it is better to give your model, fitted model. Okay. So I have given here fitted model, then I have given my treatment. What is my treatment? What my treatment is TRT. So I have given my TRT. Then my alpha I have given, I want to make group, I want to get my result on the console. So I run one, and this is the most important thing for ANOVA, for design.
నేను కోటే పెట్టుకున్నాను రెండు ఒకేసారి పెట్టుకున్నాను లేదు
Okay. So here you will get the MSE, mean sum of is mean square error, basically this value 78.56, and you will get the mean of each of your treatment, standard error, lower means confidence interval. Then you will get the critical T value, and this is the what basically you require when you have to report your CD value. This is what you call CD value. Okay, least significance difference value, CD value 12.93 here. And when you do pairwise comparison, how many, if you have 8 treatment, here we have 8 treatment, you will have 8 say 2 pairs. Okay, you will have 28 comparisons. If you do pairwise comparison with 8 treatments, you will have 28 pairs. So if you want to represent 28 pairs one by one, it will take a very lot of, means it will take too much of space. Okay, and so we do this type of grouping. Interpretation of this grouping is the treatment which have same type of alphabet, they are not significantly different. Here it is written, treatment with same letter are not significantly different, and the treatment with same letter, treatment with different letter are significantly different. Okay, so like this, these 4 treatment T6, T2, T4, T7, they all share A. So that means they are not significantly different from each other. T6 is not significantly different from T2, T4, T7, like that. Okay, so this is very simple and very effective representation of pairwise comparison. And you can also plot this like this. Okay, your treatments and your dependent variable and your plots. The dots are your mean and these are your standard error. So I think this is very effective representation of your pairwise comparison. You must use it in your papers or any type of presentation, whatever you want to do. This is very good. Then we have Duncan test. Again, very simple command, Duncan.test. Duncan, again same type of comparison, but in Duncan the difference is you don't get one value. That is the difference between Duncan test and CRD value. You get different range on the basis of the distance between your treatment groups. So here we have 7 I think range, and similarly you will get this type of grouping, different type of grouping from the LSD. And we have then Tukey test, Tukey HST. So this will give you the one by one comparison. This, like I told, 28 comparisons, T2 with T1, T3 with T1, like this, and you'll get the p value. Whichever the p value less than 0.05, you can say that that pair is significantly different. Otherwise, they are not significantly different. So all 3 types of pairwise comparison you can do as per your convenience. Then we have RBD. In RBD, instead of one factor, you will have both factor, treatment plus replication. So grain yield followed by treatment plus replication, and our data plant character. I will run the command. I will get the ANOVA table, treatment, replication, residual, and again same thing, LST pairwise comparison. So I got this comparison again for RBD. Here you get the LST here, and this is pairwise comparison. Same thing you can do with Duncan, and this is what you call. So RBD, and difference only is your this you have to add replication in RBD command. First in CRD you just have the treatment, grain yield followed by treatment. Here you have grain yield followed by treatment plus replication. Whatever your model in theoretical model is there, you have to write just here. Okay. Then we have our factorial data, factorial more than one factor as our main factor. So we have fact data. Again it is stopped. Okay, this is my fact data. Okay, my fact data. So here we have variable A, B, replication and yield. This is combination, basically one convenience variable I have made, not necessarily required. You only have to understand these 2 variables, A, B, replication and yield. So like I told, first I have to declare all the factors as factor. So I declared my A factor as factor, B as factor, and replication also as factor. Then I got the this structure. I have 3 factors and 1 dependent variable, which is my numeric variable. Okay, now you see this command, we have y variable y followed by replication or block. Then this is how you write your means different combination of factors. If you write a star b, it understand that a plus b plus a interaction b.
ఏముందండి అందులో ఏమన్నా అంతలా సౌండ్ చేసేస్తున్నా
So here you can see that means all the combination of a and b, either you can write like this or you can write like this. And both are the similar thing, a plus b plus a interaction b. So you can use any of them, both the commands. So you run any of them, it will give you the similar thing and you'll get the ANOVA. So replication, a factor, b factor, a interaction b, and residual. This is your basic factorial design, two factor design. If you have three factor design, you do the same thing, a b c. Whatever the interaction you want to give, you can write here, a plus b plus c plus ab plus ac plus bc plus abc. Whatever you want to write, you can write here and you'll get the ANOVA. Okay, so this is very flexible. Whatever you want, you can write here. You just have to understand your theoretical model. What is your theoretical model? So we got the summary. Then again, you can get your uh, multiple comparison result. I have 4 levels of A, so I got 4 groups A, B. These two are significantly not significantly different, but A4 and A2 are significantly different. So like this, you can make groups. You have got here your CD value. Similarly, you got for your B. Okay, so you got for your B. You have 3 levels of B. You got your grouping. Now, for interaction also, you can have your pairwise comparison. For that, you will have to do a little bit of coding. I have given here, you can try by yourself. I think you will get it. I will just run it. I'm running out of time. So this is how you will get your pairwise comparison coding, a pairwise comparison for A and B. I have used that combination for my pairwise comparison. Like you have 4 into 3, 12 combination of treatment A into B. So I have used that combination variable for getting my pairwise comparison C1 to C12. So that's why I given that variable. You can use that way, or you can use this thing, A into B also. Out AB, out AB. So you can get like this also, A4 with B3, A3 with B3, like this you can give. These two are the same. These two are same, 8.98, 7.2, 8.98, 7.2. So you can use any of them. Okay. So this is how you write for pairwise comparison. Okay. Then split plot, we have the split plot data. Again, one is main plot, subplot. So yes, the command for split plot is sp-plot. Okay, this with command I want to tell you. This with basically you want to say that I want to do this analysis with my fact data. To understand this one, I have with command, I want to use this fact data and I want to do this analysis. So that's how I have written here also. With fact data, I want to do this type of analysis. Please mute others who are not speaking.
అలా ఉంది కదా
Okay, so this sp-plot command is used for my split plot design. With fact data, you can use replication, A, B, yield. It is, again, I told you use this help, you will understand how I have written this. See, first you have to give block, you have to give main plot factor, then you have to give your subplot factor, then you will have to give y. So this is my block, this is my main plot factor, this is my subplot factor, and this is my y. So I run this and I will get my result. Split plot, block A, error A, B, AB, and error B. Okay, so this is my split plot. Again, you can get all type of pairwise comparison here. A pairwise comparison for A, pairwise comparison for B, pairwise comparison for AB. With both approach, this is my second approach. You can use your, you can say model approach, not necessarily required if you're using this command. So I will leave it here. And this is a split plot, a strip plot. So for a strip plot, it is just a strip plot. Here for a split plot, it is a SP plot. So I will run this one. And this is your strip plot ANOVA. Replication A, B, error B, AB, and error C. So this is your strip plot ANOVA. You can get your pairwise comparison like this. I have not written, see, to get the result, you will have to write like this, out A. You will have to recall the thing. Okay. So here you are getting pairwise comparison for A. Here you will get pairwise comparison for pairwise comparison for B, like this. And you will have to recall the thing. Like this. So strip plot, split plot, it is very simple command with agricoli package, sp plot and strip plot package. Sp plot and strip plot. And there are various type of plotting you can do. You can plot error bars. First, let me plot this one. This I have already told, you can use them. And also you can plot this type of bar plots with your standard error of means like this. You can use any of them. You can see these commands, you can practice. It will be better if you practice by yourself. Try to understand the things. I have most of the things I have explained what we are going to do in this by using the comment. Okay. Okay, so I think sir, design also
Yeah.
completed. Any questions?
Any questions? And this coding and all the presentations were already shared to the organizers. And I think if anyone is not getting, I think they may send tomorrow or tonight. Don't worry, we'll share all the coding and presentations to each and everyone who registered for this workshop. I am so happy. My teacher, Dr. L. Venkateswara garu, was also there in the workshop. I think he's looking after the and all these things. And I request him to give his remarks.
Sir, sorry to interrupt. Should I stop presenting?
Yeah. If you want to do anything more.
No, sir, I think I have completed the topics.
Yeah. That's why. Thank you. More than what we requested, you covered, including split plot, strip plot, and also the factorial.
Yes.
And if anyone wants to ask any questions, you please unmute yourself and ask the questions. Yeah, there is one question. What is the difference between correlation and regression?
Okay, I think I told it at that time. Correlation just gives you the idea of relationship between two variables, whether it is positively related, whether they are positively related or negatively related, highly correlated or means weak correlated. You just get the idea. But regression gives you the exact relationship, how much y is varying with the change in x variable, how much depend, what is the change in dependent variable with the change in x variable, independent variable. That is the regression.
Is there any other questions?
I think
No,
someone is.
no, no, it may not be possible. You need R coding, no, R software is should be installed.
It is a computer software you cannot do
Yes.
in mobile.
Yeah, Android, it may not be supported. Is any other? Otherwise, I thank Mr. Akhilesh Kumar Singh, Akhilesh Kumar Gupta, because his guide is Akhilesh Kumar Singh, head of the department, IGKV Raipur. And we thank both of them because of him only Dr. Mr. Akhilesh Kumar Gupta came to Bapatla to complete his master's program. And I once again thank Dr. Mr. Akhilesh Kumar Gupta for your nice presentation
Thank you, sir.
and
Thank you, sir.
good
All because
coding
of
and
you, sir.
without wasting even a single minute, you covered all the things and made it very easy how to get the data from Excel to this R coding. So it is so nice. I think all the participants are going to be benefited with your lecture, and we are going to provide all the codes to each and every participant. And I once again thank to the organizers for their nice presentation. Organizing such a good workshop. And I also requested you, all the participants, tomorrow at sharp 11:30. The second day's first session is going to be started by, that is by Dr. Santosh Rathod. There is a small change in the program. By earlier in the brochure, it was multivariate techniques, but because of Dr. Sushil Kumar Sarkar, who is busy with some other meeting, so you want to take afternoon session. That's why Dr. Santosh Rathod is going to take the forecasting techniques. So it is very, very interesting and is also from ICR institution working at Hyderabad. Really, it is also is a very, very experienced faculty. So I request you all to be sharp by 11:30. Tomorrow we are going to start the first session. So with these few remarks, I once again thank Mr. Akhilesh Kumar Gupta for his nice presentation.
Thank you, sir. Thank you for giving me the opportunity.
Thank you. Thank you.